Okay, in this video we're going to analyze the boost converter. However, this time we will include semiconductor losses as far as the diode and transistor are concerned. We won't be looking at the equivalent series resistance of the capacitor just yet. But this method is pretty much a lot different than the version with no losses, which is right here. As you can see, the formula for the output voltage is this simple little thing, but again, that's assuming all ideal components. And for this one, however, you get something that looks more like that, and I'll explain all of this as best as I can. Alright, so here's a circuit for your boost converter. You got your inductor, your diode, your MOSFET. Specifically in this case, it's an N-channel MOSFET. Here's your gate drive, circuitry, your capacitor, your resistors, and here is your output voltage. This is the current going through the capacitor, and here's the current, or the main current that's gonna come through here, and eventually split between these two. Now, if we want to model this in a sort of way where we include the losses, we have to develop these equivalent models. So the MOSFET model is going to be basically a switch with an on resistance, because as you know, a MOSFET, when it's turned on, it basically makes a short over here, but there is a tiny amount of resistance that you should account for, especially because ultimately at the end you'll have to deal with switching losses and all that stuff, but that's a whole different video. So we're going to model the MOSFET as a switch with an on resistance. The diode is going to be, since the diode has a voltage drop over it, across it, I mean, that tends to be 0.5, 0.6, even up to 0.1 for like Schottky diodes. It depends on the diode. So we're going to model the diode as basically a little voltage source or voltage drop with a resistance, because it does have some, if it's dropping voltage, that means there's a resistance across it. So it's a voltage drop with a resistance. And since the diode does turn on and off, within our circuit, we also have to model it as a switch. So given that much, we know that the duty cycle here is going to turn on the MOSFET at some point and then turn it off at some point. So we're going to model the circuit at different states of that MOSFET. So when that MOSFET is on, oh yeah, I forgot, where did I put that? The inductor resistance. Oh, here it is. The inductor is nothing more than, a piece of wire, or the inductor with a resistance, which is the resistance in that wire. So we model the inductor as an inductor in series with a resistance. Doesn't matter if you put this first and then that over here. In any of these, the order doesn't matter. It's the point that they have some sort of loss. So anyways, so when the MOSFET is on, what you have is your voltage source, obviously, and then the MOSFET is on, so you're going to have the inductor, and then your circuit is going to go this way, as you can see here. So you have your inductor in series with the inductor resistance in series with the on resistance of the MOSFET. And then the capacitor part, this part of the circuit, just becomes like its own little loop where the capacitor is discharging through the resistor, so you have a current going this way. Now when your MOSFET is off, basically this entire leg of the circuit disappears because it's off, so it's in open over here, and you just have this. So that's nothing more than obviously your inductor resistance and your inductor in series, the voltage drop across the diode in series with the resistance of the diode, and obviously your main current that's coming through here is now split. It's charging up the capacitor, right? And it's also splitting to the output here, or the load resistor, and obviously your output voltage is over here. So given these two equivalent circuits of the MOSFET either on or off, we can draw the waveforms. So the voltage across the inductor, maybe I should make this smaller so it all fits. So the voltage across the inductor during the MOSFET on period, which is when the duty cycle is on, your on time, right? Your DT, your duty cycle times your switching period. So I'm going to explain, I guess, some of these labels. Here's your duty cycle times your switching period. This is your T, your period. And here's d prime of T, which is, the remaining time of the period. So during in other words, this is the on time, this is the off time for the MOSFET. So during DT, what is the voltage? Because right now we're going to do the waveform for the voltage of the inductor. So what's the voltage of the inductor during this period? Well, it's nothing more than obviously the voltage source minus the voltage across this resistor, which is nothing more than current, right, times resistance. That'll give you that voltage drop, and then current times that resistance will give you this voltage drop. So the voltage drop on the inductor is going to be this minus this voltage drop minus that voltage drop. So the inductor voltage is going to go up to this voltage up here, which is Vs minus IRL minus IR on. Now during the other half of the period, it's your inductor voltage is again going to be Vs minus this minus that voltage drop minus that voltage drop, and ultimately minus that voltage drop. So as you can see right here, so during D prime, this is the voltage of your inductor. Now what's the current waveform for the capacitor? Well, when the capacitor is during this part, the capacitor is discharging. So the current, so when a capacitor is discharging, the current is said to be negative, as opposed to when the capacitor is charging, the current is said to be positive. So the current here is going to be negative. Well, what's the current? Well, the current is basically, since this is basically a series little circuit here, the current is nothing more than whatever voltage is here divided by resistance, right? That'll give us current. So it's going to be negative V over R, as you can see right here. And this is during that same period during the on time. During the off time, when the MOSFET is off, this period, the current here is basically this main current that splits between the capacitor and this output here. So it's going to be this current minus that current, and it's going to be positive because at this point, as you can see, the capacitor is charging. So it's that main current minus the V over R. And now that we have this capacitor current and voltage and inductor voltage, we can do what they call the volt-second balance, where we take the average voltage of the inductor, and we find a formula for it, and we set it equal to 0. Because we have to set it equal to 0 because that's what's going to make the inductor voltage balance and not go up to infinity. So the average voltage across the inductor has to be 0. So we're going to find the formula for the average inductor voltage, which is nothing more than the area of this curve, which is basically this rectangle, plus the area of this rectangle, all divided by your period, your T. So that looks like this, right? Well, what's the area of this rectangle? Well, here's the width, right, dt, and the height is up here, which is Vs IRL minus IRL IR on. So we're going to multiply those two to get that first area, right? So dt multiplied by that, and then we're going to add that to that. We're going to add the area of this rectangle, which is d prime of t multiplied by its height, which is this. So we have the average inductor voltage is the area of the two divided by the period. Now, if you look carefully, there's a t term here and a t term here, so we can factor a t out, right, and just leave everything else. But then that t will cancel with this t, so then all the t's cancel out. So much cleaner now. It's just we'll have no t's, so then we just distribute this d to this term and to this term, as you can see right here. And then over here, again, we have no t's because they canceled out, so we distribute the d prime to all the terms. And so now here's something interesting. So we're gonna combine like terms, right? Now d and d prime are related to each other, right? Because I think I wrote it here. So d is a percentage. Obviously, it's your duty cycle. So if you want something to be on half the time, you give it a 50% duty cycle, and percentage is expressed as a number between 0 and 1. And d prime is nothing more than the remaining. So if you have a duty cycle of 25%, that's 0.25. The remaining is 0.75, right? Now if you add d and d prime, you get 1, because 0.25 plus 0.75 is 1. So d and d prime, d plus d prime equals 1. So when we combine like terms over here, this dvs and d prime vs, those d and d prime are going to be 1, so you just get vs. And same thing with the IRL, the current times the voltage here that you get when you multiply the current times the resistance of the inductor. The other one over here has d prime, so then you're going to have just IRL. Now the on resistance, there's no other term here that has d prime IR on. See, so this one stays as just d times I times R on. Now this dvs, d prime, oh, we already took care of that, sorry. We already took care of that also. So then what's left is this, which again, it has no other term with just d in it, so then it stays. And then this one also has no other terms, and that has no other terms, so they all stay. So that's your equation for the average voltage across the inductor, and we have to equate that to 0 again, because we must force the average inductor voltage to be 0. So we're going to solve as if everything were equal to 0. We cannot have any constant number over here like 4 or anything like that, because otherwise our voltage waveform will go to infinity, and that's not what we want. So anyways, so the average capacitor current. Well, another thing I wanted to explain, actually no, I'll explain that in the, should I explain it now? Yeah. Okay, so if you look at the average inductor formula, where you have the VG and the IRL no longer have any D or D prime on it, that makes sense, right? VG, why do I call it VG? VS. That makes sense that these two things no longer have a D or D prime on it. Why? Because the voltage, the voltage across coming from the source, it's always there, regardless of whether the MOSFET is on or off, whether we are at D or D prime of T. There's always voltage coming out of there, and there's always voltage going through the inductor and its equivalent resistance. So it makes sense that that term is there no matter V or D, right? And the IR on, which is the current times the on resistance of the MOSFET, that has a term of D, which is just your this when the MOSFET is on. So that makes sense that we only put the on resistance. The on resistance is a function of just when the MOSFET is on, just this time, which is D. Because obviously if the MOSFET is off, why are we going to include that resistor into our formula, right? So that's why that R-on MOSFET, that R-on term is has a product of D. And the same thing with the rest of the things in the circuit. You see all these things, the voltage drop across the diode, the resistance of the diode, and the voltage output. All those things have a term of D prime. Well, those things are only really visible in our output when the MOSFET is off. So there's no reason why they should be in the equation of when the MOSFET is on. So that's where they have a their terms of D prime. So now if we look at our average capacitor current, the average capacitor current is, for the on time, right? The capacitor is this is the MOSFET on. The capacitor is not connected to anything here, so the current is basically it's discharging through the resistor, so it's a negative current. Well, what's the current? Again, it's going to be the voltage over resistance that will give us the current. So during the on time of the MOSFET, our capacitor current, IC, is negative V over R. During this time when the MOSFET is off, the current is now basically splitting between this and this. So then we have this we have this where the capacitor current during the off time is nothing but this main current minus this current will give us this current. So you can see that right there. And we got that from, well, here's the so again, so to find the average capacitor current, we're gonna do the same thing as we did for the inductor, where we find this area, you multiply by that, you find that area, multiply by that, and you get this sort of thing. And the same thing happens where you have this D with this negative VR, and then you factor in this D prime with this negative V over R. So then this has a D prime term, and this has a D term, so that they'll just equal 1. So then you just end up with negative V over R. The I doesn't have any term with the regular D, so then that stays. So then you have D prime times I minus V over R, and that's the formula. Again, you have to equal this to 0. That's the average inductor, because I keep saying this I, and I want to say inductor current, but it's the current of the capacitor. So that's the average capacitor current. Now we can take this formula, the average voltage across the inductor, and this average capacitor current, and we can make an equivalent circuit now. Okay, so the equivalent circuit will look like this. The equivalent circuit, given this basically this transfer function, is this. It's a loop equation basically. So then you're just gonna follow it from left to right. So you have a voltage source, and you're gonna subtract another voltage which is given by a resistor. So you have an RL, and you're gonna subtract another resistance here by DR on. This is the R-on of the MOSFET. That's the only dependent on the on the on time of the duty cycle. Then you're gonna have this voltage drop across the diode, right? Since that's a constant voltage that it's gonna give us, we put that as a voltage source, right? Because if you notice, all of these are components as R's and D's. As R's, so they're all resistors, and this one is actually a voltage, so we're going to put that as a voltage source, or voltage drop rather, and it's D prime of VD. And then we have the resistance of the diode itself, so that's going to be D prime. It should have no I there, just RD. because it's a resistor, so it's just that. So there's that, and then we have this voltage, which is I should have put d prime of d. I mean d prime of v. Yeah. So sorry, I'm drawing with my mouse now because I did this on the laptop. So then that's the equivalent circuit that we have for given this equation. Now we could do the same thing with the capacitor. The capacitor will have its equivalent circuit, which is nothing more than a current source. A current source that's given by d prime of I, and then a resistor, which is basically going to have a voltage drop across of it, and there's a current going through here. Now we can put these all together using the transformer model, and there's another video I did on that. How do I zoom out? Holy cow. Anyway, so there's this, so we can put these two together and you get this. Basically you, oh crap, you have a, hold on, I need to pause this because I really need to zoom out. Yeah, it was under view the whole time. Anyways, so yeah, we put these two together, and basically you just kind of join them right here, and in place of these two things you put this sort of transformer whose turn ratio is d prime to 1, right? And I'll make a whole, if not, I should already, I'll make a, there should be a video because I'm going to upload these videos in order. So there's a video on how do you, what the deal is with this transformer model and what it means and why this is here. So you can watch that if you haven't already. So now this becomes your, I guess, your equivalent circuit. So if we want to make life simpler for ourselves, basically, what we're going to do is, first we're going to combine these things, right? Let's combine some of these just to make it simpler. So since this is a voltage drop and here's our voltage source, we can just combine those and put voltage source minus that voltage drop, which is d prime of Vd. So that becomes our new quote-unquote source. And these are all series resistors, so we can just add them up. So we're going to have an equivalent resistance of RL plus DRon plus D prime RD. Okay, there's nothing to simplify on this side, so then you have this. Now, to make this easier to solve, because remember we're trying to solve for the output voltage given all the losses and everything. So what you do is you're going to bring this all over to this side and just make it one circuit without a transformer. And when you bring the voltage source over, you basically divide by this. When you bring the resistance over, you divide by this squared. So you're going to have that Vs minus dVd divided by d prime, and you're going to have your R equivalent divided by d prime squared and your R. Now, given this, if you ignore the fact that, you know, this is a fraction and other stuff, how would you find this output voltage right here? Well, it's a simple voltage divider, right? Where it's the voltage source times this resistance over this resistance plus this resistance. So that gives you that the output voltage V is nothing more than Vs minus d prime of Vd over d prime times that resistance over that resistance plus Re over d prime squared. And that's basically your output voltage. That's how you find your output voltage given all the losses and the equivalent resistance of the inductor, the MOSFET, the voltage drop, and resistance of the diode. So I hope this made sense, and that you understood it. If not, you can ask me questions. Again, I'm just learning these things, and I'm trying to make videos so that I can explain it in my own words to make sure that I understand it as well. So if you have some really off the wall question of something more advanced than this, I probably won't know the answer yet. But if you have any questions about what was done here, I should be able to answer it. I hope I can. So let me know.